Alright, silly people, here's the situation. We are going to be finding the eigenfrequencies of this configuration of springs using the action angle variable method. This is actually a chapter 6 problem where if you use the theory of small oscillations, you could get the same results. But this is just a flourish of doing it in action angle variables and having to perform a canonical transformation on the system in order to do that. So I've defined these positions of these masses here as x1 plus a and x2 plus 2a, much like I was doing in chapter 6. That's just so that we can have nice cancellation in the potential terms. So first thing we have to do is construct a Hamiltonian, which should be fine. We'll start from the Lagrangian just to be complete. The kinetic energy will be m over 2 eta 1 dot squared plus eta 2 dot squared. A isn't actually changing. The A's are all constant, so we'll just go ahead and call that x1 dot squared plus x2 dot squared. With little trouble. Oh, I wasn't actually recording any of that. Hold on. But there it is. So that I haven't done much so far. That's what it looks like. So the next bit is to find the potential, which is gonna turn out to be kind of obnoxious. So this is gonna be some spring potentials for the first one and the second one. So there's actually 3 terms in the potential, right? Because there are 3 springs. So there's going to be, I'm going to call this one spring 1, spring 2, and spring 3. So the potential for spring 1 is going to be k over 2 x1 plus a, the position of the mass, minus a, the equilibrium position squared, which is going to be just k over 2 x1 squared. The potential of the second, or I will do the third spring because it's simpler. Potential of the third spring, also just a Hooke's law potential, which is going to be k over 2 x2 plus 2a minus 2a squared, which is just going to be k over 2 x2 squared. That's gross. x2 squared. Fantastic. Then for the third spring, or for the middle spring, S2, it's going to be literally also a Hooke's law potential, except now you have 3k over 2 out front. And then in the middle, it's the distance between x2 and x1, or actually it's the distance from eta 2 to eta 1. So that is 2a plus x2 minus x1 minus a, and then minus the equilibrium positions of either one. So it's going to be minus 2a plus a. Should just give you x2 minus x1 squared. All right. Adding all those together, the potential is giving k over 2 x1 squared plus x2 squared plus 3k over 2 x2 minus x1 squared. This is when the canonical transformation happens. So right now the potential is in a form that is not separable. You're going to have cross terms between x1 and x2, and so solving it in action angle variables is currently impossible. But to make it possible, we can do the following canonical transformations. defining a new pair of variables called y1 and y2, which are going to be x1 plus x2 over root 2, and y2 being x1 minus x2 over root 2. Now let me show you how these things work. It's going to be x2 is equal to root 2 y1 minus x1. And I'll plug that into the other equation. y2 is equal to x1 minus root 2 y1 plus x1 all over root 2. And so we have 2x1 minus root 2 y1 over root 2. I'm actually just going to write it like this. Root 2 x1 minus y1 is equal to y2. Let's solve that for x1. So that we'll have x1 equals y2 plus y1 divided by square root of 2. Awesome. Then let's use this guy to solve for x2, which will be it's root 2 times y1 minus x1. And then we can just make it so that these things have the same denominator. So we'll have 2y1 minus y2 minus y1 over root 2, which is just y1 minus y2 over root 2. Okay, so that wasn't entirely necessary. These things are pretty similar. So we'll just plug these into our form of the potential, which will be k over 2. This is going to be y1 minus y2 squared over 2 plus y2 plus y1 squared over 2 there, and then 3k over 2. Just going to go ahead and make the substitution that x2 minus x1 is equal to minus root 2 y2. Yeah, so minus root 2 y2 down there squared. And we'll go ahead and expand these guys inside of the parentheses. I'm going to factor out that factor 2. We'll have y1 squared plus y2 squared minus 2y1 y2 plus y1 squared plus y2 squared plus 2y1 y2. So the cross terms are going to cancel out. We'll have on the other end of the thing, the 2 will cancel out. It's just going to be 3k y2 squared over there. Cross terms go bye-bye. And we'll factor 2 out again. So we'll just have k over 2 y1 squared plus y2 squared. 3k y2 squared. Alright, so now we have kinetic energy and potential energy. We can go ahead and make our Lagrangian. The m over 2 x1 dot squared plus x2 dot squared minus k over 2 y1 squared plus y2 squared minus 3k y2 squared. Right. Then the canonical momentum P1 will be defined as the partial of the Lagrangian with respect to x1 dot it'll just be mx1 dot, which we can go ahead and solve for that for reasons that will become apparent. That's going to be p1 over m. And then p2 will be del L del x2 dot, which is going to be mx2 dot, which will solve for x2 dot, and we'll have p2 over m. Let's construct the Hamiltonian then. So, well, no, let's first rewrite the Lagrangian in terms of the momentum. So we'll have m over 2 there. We have p1 squared over m squared plus p2 squared over m squared minus k over 2 y1 squared plus y2 squared minus 3k y2 squared. Then let's just make it look pretty. Both of these are just p squared over 2m plus p2 squared 2m minus k over 2 y1 squared plus y2 squared minus 3k y2 squared. Now we can construct the Hamiltonian, which is going to be p1 x1 dot plus p2 x2 dot minus the Lagrangian. We've already solved for p1 and x1 dot, so we'll just put that in some good terms. So that's going to be p1 squared over m, p2 squared over m minus all of this stuff from before. I'm just going to copy it over. Boom, 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 boom. So, all in all, it's going to be p1 squared over 2m plus p2 squared over 2m minus, or actually plus, k over 2 y1 squared plus y2 squared minus 3k y2 squared, 3 squared as well. That should be plus. All right, we have a Hamiltonian. It already looks a lot like that for a simple harmonic oscillator, so solving this in action angle variables shouldn't be that difficult. So this Hamiltonian is separable, which means to find the eigenfrequencies, in the end, we're going to be finding the eigenfrequencies by taking the partial of the Hamiltonian with respect to two different actions, J1 and J2. But there's only going to be one Hamiltonian. J1 and J2 will be calculated by integrating the canonical momenta over the corresponding variables. So it'll be integrating P1 dy1 and P2 dy2. Okay, so because the Hamiltonian is separable, we can write the Hamilton's characteristic function, or principal function actually, that's Hamilton's principal function S. It will be some function of p of y1 and then some function of y2 and then minus alpha 1 t minus alpha 2 t, right? Normally we would then redefine the momenta in terms of the partial derivatives of the characteristic functions w1 and w2, but there's no need to do that. We're just going to leave it as p in this case, and so the Hamilton-Jacobi equation will read like this. It's going to be p1 over 2m plus p2 squared over 2m plus k over 2 y1 squared plus y2 squared plus 3ky2 squared is equal to alpha 1 plus alpha 2. Fantastic. So then we can actually separate this into two different integrals that we can solve. So just keeping the terms dependent on y1, we're going to have p1 squared over 2m plus k over 2 y1 squared equals alpha 1. And then solve for p, which is going to be 2m alpha 1 minus km y1 squared, all under a square root. This can be, so that's the canonical momentum, then the action will be the integral of that over a loop with respect to y1. Now I'm not gonna write the bounds of this because they kind of don't matter, because I'm just gonna make a substitution anyway, where y1 will become it'll be 2m alpha 1 over km under a radicand times sine theta. And so dy1 when we make this substitution will be root 2m alpha 1 over km cosine theta d theta. So we'll rewrite the action integral as this stuff, 2m alpha 1 over k1, not k1, km. Ha! Just there. And on the inside of the integral we have cosine theta square root 2m alpha 1 minus 2m alpha 1 sine squared theta d theta. We can also now just factor out the 2m alpha 1 from the integrand. So we'll have on the outside 2m alpha 1, which is going to be 1 over root km right? It's going to be cosine of 1 minus sine squared theta d theta. Now, if you know your trig identity, you know that that's just going to be cosine. So we're actually just integrating cosine squared theta d theta. Over a closed loop will just be, you know, it's just going to be pi. So the action ends up being 2 pi m alpha 1 square root 1 over km. Do that. This is J1. We're going to have to do partial derivatives on the Hamiltonian of the actions. So we need to actually solve for alpha. So it's going to be J1 over 2 pi m. And then up top is going to be k over m, or root km. Yeah. All right, continuing. Separating our Hamiltonian with the Hamilton-Jacobi equation, we're just keeping the stuff that depends on y2. p2 squared over 2m plus k over 2 y1 squared plus 3k over 2. That's actually meant to be a 2 squared, y2 squared equals alpha 2, right? Yeah, okay. Actually, no, not 3k over 2, it's just 3k. Let's just collect those y2 terms actually. 3k plus k over 2 is 6k, so 7k over 2. y2 squared equals alpha 2. And this integral is actually going to be really similar to the one that we did before. So p2 is equal to m alpha 2 minus 7km y2 squared, square rooted. So the action J2 will just be the integral of that with respect to y2. Over a loop dy2. Making a similar substitution as before, we'll now have y2 equals 2m alpha 2 over 7km under a radicand times sine theta. The derivative of which, or the, you know what it is. Differential, that's the word I was looking for. The differential of that. Terrible, terrible radicand. Yes, cosine theta d theta. Let's plug it in. So J2 equals square root 2m alpha 2 over 7km. And then we have on the inside cosine theta 2m alpha 2 minus 2m alpha 2 sine squared theta d theta. Factor out that square root of 2m alpha 2, so we'll have 2m alpha 2 1 over root 7km. Integral of cosine theta 1 minus sine squared theta d theta, which I'll just write this out explicitly. That's just going to be cosine squared theta d theta, which is pi root 7km. That's the action J2. Let's solve for the alpha 2, which is going to be J2 times the square root of 7km divided by 2 pi m alpha 2. It's a gross looking pi. 2 pi. Right, so now we can express our total energy, which was alpha 1 plus alpha 2, which is a representation of the Hamiltonian, as what was it, J1 root km divided by 2 pi alpha 1 plus J2 root 7km times 2 pi alpha 2. And both of those should have m on the bottom as well. Masses. Right? Yeah, okay. So again, to calculate the eigenfrequencies, it's going to be del H, del J1. We shouldn't put alphas in here. what am I thinking? Yeah, no alphas there, just 2 pi m. So then that's going to be root k over m, root km over m. Yep. Which you can turn that into an angular frequency. So this is currently a linear frequency. If you want to turn it into an angular frequency, you can. That's just going to be multiplying it by 2 pi. Omega 1 is equal to 2 pi nu 1. So that's just going to be simplifying the radical terms. It's root k over m. Hey, that's pretty familiar. That's just the eigenfrequency for the regular harmonic oscillator. That's omega. So let's see if this holds up with the other one. Nu 2 is equal to del h del j2, which is going to be 1 over 2 pi root 7 km over m and then we'll turn that into an angular frequency and simplify the radicand to have 7k over m. If you did this same problem in chapter 6, you will recognize that those are in fact the eigenfrequencies.